Welcome to this explainer. Today, we're going on a bit of a journey, a data detective journey, actually. We are unpacking Competency 004B, which is all about identifying patterns within scientific observations and data. But listen, we aren't just going to sit here and talk theory. We're going to actively model real-time scientific thinking. We'll look at raw data, think aloud, and figure out exactly how to guide your students from staring completely blankly at a spreadsheet to actually constructing brilliant evidence-based predictions. So, grab your magnifying glass and let's get ready to channel that inner detective.
Okay, let's dive into this. Here is our roadmap for mastering the topic. We're going to cover spotting hidden scientific patterns, thinking aloud to find regularity, building evidence-based explanations, making and testing predictions, and finally, scaffolding student success.
Let's jump into Section 1, Spotting Hidden Scientific Patterns, moving from simple observation to recognizing regularity.
To a novice, the natural world can seem, completely chaotic. The wind blows, temperatures fluctuate wildly, animals just seem to behave unpredictably. But science is essentially the process of looking closely enough at all that chaos to realize it's not actually chaotic at all. There are rules. A pattern is literally defined as recognizable regularities or repetitions in nature. And identifying these regularities, that is the absolute fundamental first step in any science classroom. Because think about it. If your students can't identify a pattern, they can't form a hypothesis, they can't build an explanation, and there is no way they can make a scientific prediction. The whole shebang starts right here.
And this brilliantly illustrates the massive cognitive leap your students actually need to make. An observation is just static. The sun is out. It's true, but it doesn't really give us any predictive power, does it? A pattern, on the other hand, is dynamic. It's continuous. The sun rises every morning. That shows repetition over time. Our goal as educators is to pull students away from those isolated, one-off observations and really guide them toward recognizing these repeating behaviors.
And the beauty is these patterns manifest across literally every single scientific discipline. In earth science, it's the absolutely predictable cycle of day and night, the seasons or moon phases. In life science, we see it when observing the repeating stages in life cycles. A plant predictably going from seed to seedling to flower. And in physical science, we see patterns in how objects respond to forces, like figuring out which specific materials consistently show magnetic attraction. The specific content changes, sure, but that underlying skill of pattern recognition, it stays exactly the same.
Moving on to Section 2, Thinking Aloud, Finding Regularity, Becoming a Data Detective. Okay, let's actually step into the shoes of a scientist for a second. I want you to experience the procedural knowledge required to make sense of this kind of information. Imagine you're a student or, heck, even a meteorologist looking at raw, messy data for the very first time. I'm going to think aloud here just to model the internal monologue of a scientist. Let's see. Monday, the pressure is dropping and the temperature is 85 but rising. Okay. Tuesday, pressure is low, temperature is 88 and still rising. Right? Wednesday, pressure is rising, but now the temperature is 82 and dropping. At first glance, my brain is just kind of bouncing between the days. I'm honestly a bit confused. Is there a relationship here? Let me look closer. Okay. When pressure goes down from Monday to Tuesday, the temperature goes up. But when the pressure starts rising on Wednesday, the temperature starts dropping. Okay, I'm actively searching for regularity, and I think I'm seeing a clear inverse relationship here. Now think about how a visual representation changes everything. Taking that raw table data and organizing it into a simple chart comparing the temperature trends with the pressure changes is a game changer. Suddenly, that hidden pattern we just had to mentally struggle to find in the raw numbers is crystal clear. When the pressure line dips, the temperature bars go up. Honestly, organizing data visually is basically the ultimate cheat code for spotting patterns.
Section 3, Building Evidence-Based Explanations, the Blueprint for Reasoning.
So spotting a pattern is really only half the battle. Next, we have to actually figure out the why. Here is that step-by-step blueprint. 1. Observe the data. 2. Identify the pattern. 3. Derive meaning from that pattern. And 4. Develop an evidence-based argument. This sequence is absolutely crucial. In fact, under the 2024 texts, this aligns perfectly with the scientific and engineering practices. Students are explicitly expected to use identified patterns to derive meaning from their data and then develop logical, evidence-based arguments that are completely consistent with scientific principles.
I really want to drive this point home. Patterns aren't just fun trivia facts. They are the structural, foundational evidence used to build strong scientific arguments. When a student asks, why does it rain, the explanation relies entirely on the identified patterns of evaporation and condensation. The pattern is the foundation. The explanation is the house built on top of it.
All right, Section 4, Making and Testing Predictions, the core value of forecasting.
Once we have an explanation based on a pattern, we unlock what is basically an incredible scientific superpower, predictive power. We move from just explaining the past to actually forecasting the future. Let's do another quick think aloud, this time focusing on forecasting. Say I'm a meteorologist looking at my instruments. Okay, I'm seeing the air pressure is dropping rapidly. At the exact same time, surface temperatures are rising significantly. Now, based on historical data, I know this specific pattern of atmospheric instability precedes major storms. Therefore, a severe weather event like a tornado or hurricane is likely imminent. See that? By understanding the pattern, I didn't just explain the current weather, I literally predicted the future weather.
But here's a crucial question for you to consider. If a prediction is made based on a pattern, how do we reinforce its scientific validity? Because, let's be real, a prediction is just a guess until it's proven, right? As a teacher, you have to provide opportunities for your students to actually test their predictions through further investigations. If a kid predicts a magnet will attract a certain metal based on a pattern they noticed, don't just say, good job. Hand them the magnet. Let them test it. When their prediction turns out to be correct, it so powerfully reinforces the validity of the underlying scientific idea.
Let's bring it all together in Section 5, Scaffolding Student Success, Instructional Strategies.
Let's zoom out from the hardcore science for a moment and focus on the pedagogy. How can you replicate this exact detective work and predictive success in your own classroom? First off, utilize data organization tools. Guide your students to use charts, bar graphs, and line graphs. Remember how much easier it was to see that pressure and temperature relationship when it was graphed out? Give your students that exact same advantage. Second, use scaffolding questions. Don't just hand them the answer. Prompt them with, hey, what patterns do you notice in the data? And once they spot it, push them even further with, okay, predict what patterns you might observe next.
So, the really crucial point here is this: patterns have boundaries. The real world is messy, and as we all know, a middle schooler's lab experiment rarely, if ever, yields a perfect smooth curve on a graph. Teaching students to recognize anomalies and identify sources of error is a critical part of the scientific process. It doesn't mean the pattern is broken, it just means our understanding needs to be refined.
I want to leave you with this final, somewhat provocative thought. Think about your next science lesson. What happens when the data your students collect simply doesn't fit the pattern you're trying to teach? Are you going to just gloss over it, or will you use it as an opportunity? How will you teach your students to handle those sources of error and become true data detectives? Mastering Competency 004B isn't just about finding the perfect pattern. It's about navigating the messy, wonderful reality of scientific discovery. Thanks so much for joining me on this explainer, and happy teaching.